All right, so last for the session, we have David Hill from Oregon State University.
Okay, thank you very much. Okay, so one of the things that we're interested in is essentially understanding the various physical processes that control nearshore and estuarine waters. And in this talk, I'll be talking a little bit about sort of almost like a direct numerical simulation modeling approach to that and to understanding how those conditions will change on the decadal scale. I'm just very briefly going to talk a bit about sort of why we're doing what we're doing, how we did it, and what we found. All right. So with regards to estuaries, and the figure is a little Oregon-centric here, so forgive me for that, but in Oregon, there's a lot of reasons for studying what's going on in estuaries. What sort of infrastructure we have on the coast is tightly clustered around estuaries like Coos Bay, Yaquina Bay, Tillamook, and so on. There's a fair bit of commerce that occurs. Obviously, the Columbia, but also Coos Bay has a port where a lot of dredging occurs to keep those shipping lanes open and so forth. Estuaries are very important from a recreation point of view as well in Oregon, and they also provide a great number of different ecosystem services. So this is sort of a complicated picture of what controls estuarine hydrodynamic processes. You can see in the middle we have the estuarine ecosystem, and it's being forced at two sides, the oceanic side and the watershed side as well. What feeds into each of those is a variety of climate change processes, weather, land use, resource management, and so on. I prefer this as a little bit of a simpler look at what is going on inside of estuarine waters. On the left-hand side, you can look at estuarine hydrodynamics from what's called a barotropic point of view, where your equations of motion are depth integrated, the hydrodynamics are simpler, faster to compute, and what you typically get out of these types of modeling approaches are things like currents and water elevations, which are important from a flooding point of view. So these are some simulations that were done into the Columbia River. We're looking at water velocities here, we're looking at inundation due to tsunami activity, those sorts of things. On the right column, you can look at estuarine hydrodynamics using baroclinic methods, where you get the full three-dimensional structure of the water column. You get information about temperature, density, salinity. So this is work that we've done up at Cook Inlet, where we've coupled some hydrologic modeling with a sort of a Gulf of Alaska-wide ROMS model to look at the patterns of, here we're looking at bottom salinity, and here we're looking at surface salinity. So what tool you use kind of depends on what you're trying to get out. This talk really focuses more on the left side, which is looking at barotropic hydrodynamics and an interest in water elevations. This just orients you a little bit about some of the basic characteristics of the hydrodynamic climate of the Pacific Northwest. The first three panels that you see, these are climatologies, so they're long-term averages by month on the horizontal axis, but the first three panels are data that come from the Stonewall Bank buoy. And you can see wind speed, significant wave height, and dominant wave period. And things are very temporally correlated. So we have strong winds in the winter, weaker winds in the summer. That leads to stronger significant wave heights, longer period waves in the winter. And again, those variables are weaker in the summer as well. The bottom panel, this is essentially a normalized hydrograph. So we took 12 or 13 streams sort of along the Oregon coast, took their long-term average hydrographs, averaged them together, and then normalized them based upon the peak flow, which occurs in the winter. And what we see is that summer flows, I did the same thing. There we go. Summer flows tend to be 3, 4, 5% of typical winter flows. So in the wintertime, these estuaries are getting hit hard from both sides in terms of strong forcing on the ocean side, strong forcing on the terrestrial side. So what we're interested in is, can we actually quantify the hydrodynamic response of estuaries to climate change? And there's different ways that you can look at this. You can interest yourself in sort of mean variables, changes in sort of mean elevations, and so on. You can focus more on extreme events, what's going to be changes to the 20, the 50-year water elevation, and so forth. So this is a project funded by Oregon Sea Grant. We're looking at Tillamook Bay and Coos Bay, and today I'll be talking just about Tillamook Bay. So to move into the methods, I want to give you a little bit of an explanation of sort of how we approach this. And this is our conceptual model. On the right-hand side, ADCIRC-SWAN is our main hydrodynamic engine. Okay, it tightly couples together a circulation model with a wave model. These models pass information back and forth at each computational time step. The arrows leading into Ad-Stirk-Swan here represent data streams from different boundary conditions. So for example, we have to force the offshore boundary of our domain with both tides, which are easy to get, and waves, which are somewhat more difficult to get. We have to force the terrestrial side with stream flow. So you can have rivers coming in at various locations in your computational domain. And then the actual free surface of your computational domain gets forced by wind stress and surface pressures. So the rest of the things that you see on the left-hand side, the global climate model, the regional climate model, and then a variety of routines that do hydrologic routing, those are all sort of preliminary steps that lead you to these sort of three main locations where boundary condition information comes in: the offshore boundary, the terrestrial boundary, and the free surface of the estuary. To begin something like this, again, to go back, Ad-Stirk-Swan is kind of the main computational tool here. Your computational grid for that has to be developed fairly carefully. This is a fairly zoomed out view. We come in a little bit more. The red boundary there is our actual computational domain. We've got Tillamook Bay. We push it fairly far offshore and also fairly far north and south of the bay itself. Coming in a bit further, you can see Tillamook Bay itself now. Right here, this is the watershed that feeds into that, and the locations of a couple of different USGS gauges, the data from which we use to help calibrate and validate our hydrologic routing. And then finally, the bathymetry of Tillamook Bay itself. It's a fairly broad bay. It's fairly shallow. It's very significant mud flats on the southern and the southeastern portions of it. Okay, so now doing a sort of a long-term historical simulation versus future, we have to make some adjustments to the bathymetry. And 80 centimeters is sort of a middle-of-the-pack value, going out to about 2070, 2080. So that was the change that we made in terms of water depth from the historical to the future simulation. With regards to the weather model, we ended up using NARCAP for this for a sort of complicated assemblage of reasons. It had the sub-daily time step that we wanted. It had the offshore coverage that we wanted. Both of those are important because we are trying to model waves that are developed by intense short-duration storms. It's got reasonable spatial coverage, so it is a dynamically downscaled product. I forget 30-some kilometers or so. And within the NARCAP project, there are two time periods available. We ended up doing a fair bit of bias correction to this using the NAR reanalysis product as a sort of our true value. And what this basically does, it's a little difficult to see here, but there's a black line here that represents the, that represents the CDF of temperature according to NAR. The red line is the historic NARCAP CDF, and you can see that it's quite a bit different. It's cooler and it's got a great deal more variance. And so we go through procedures with all of our variables to adjust the mean and to adjust the variance so that NARCAP is brought into agreement with NAR for the historic period. And then we do that same adjustment process for the future data. Over here is showing you climatologies of a variety of variables. And again, you see black, that's NAR, for example. That's our target. The blue here is NARCAP, and you can see it's quite a bit cooler in the winter time. And the bias correction process gives you these green circles, which match up quite nicely. So with the slight exception of the wind direction was one thing that we had a bit of difficulty with. Excuse me. Okay, let's go through these boundary conditions. Offshore waves, that was a fairly cumbersome one to do. We actually had to run a Pacific Ocean scale Wave Watch 3 model to be able to generate the wave conditions, and here I'm talking about wave directions, wave periods, wave amplitudes, to force our Tillamook Bay model. Stream flow. Okay. Again, we took basically our climate products and we run them through a variety. We use Glenn's list and series of codes, Micromet, Snow Model, and HydroFlow, to take this data, distribute it to a high-resolution, run it through any relevant snowpack processes, and then route that down to Tillamook Bay itself. These are three of the USGS gauges for which we were able to get data, and you can see the comparison between the observations in the black and the predictions in the red are fairly good. We're coming in a little bit low on the volumes. We're not quite getting the peaks, but the temporal response is really, really excellent. Okay, so a few words about what did we find. So a couple of things. These are a couple of slides on changes to mean variables. So this is looking at the offshore wave climate. And here we're looking at the significant wave height and the mean wave period. And in the blue, we see the historical. So again, this is kind of what we expect for the Pacific Northwest. Very large waves in the wintertime, much smaller. And in the future, what we are seeing here is in kind of the, I'd say, late winter, early spring, somewhat lower wave heights. And again, these are mean, so this doesn't really reflect the variability. And in the sort of early winter, slightly higher wave heights. Okay? And the mean wave period pretty much is showing that all throughout the year we're going to have slight reductions in wave period. Okay, so now why do these big offshore waves matter when it comes to something like Tillamook Bay, which has a fairly narrow inlet? All right, there's not a lot of penetration of these big waves. And so if you're interested in what's going on inside estuaries, are you going to have flooding, you might be thinking that these waves don't really matter. But what happens is when the very large storm waves in the winter approach and break, that leads to the generation of what's called radiation stress gradients. And that has the ability to push water into the bay. So during really extreme storms in the Pacific Northwest, you can get up to 1.5 meters, okay, of what's called non-tidal residual or storm tide that's pushed into the estuary. And it's due to waves. You don't see those waves when you're in the estuary. Okay? So that's why this boundary condition is a really important one to nail down correctly. Changes in mean stream flow. Again, this is just mean, not variability. Fairly similar to what we see in the patterns for the wave height. In the kind of late winter, early spring, slight reductions. And then we do see a few months into the winter where we have larger flows coming into Tillamook Bay. And then finally, water levels. Okay, so this is the main product of this particular piece of work. We're interested in water elevations. We're interested in flooding. What are going to be the changes in flooding and so forth. So what we're looking at here, the top two panels are the historic. Okay, and this is just at one particular grid point. All right, so what you have to remember is that we've got this computational grid which is made up of tens of thousands of grid points. And at every single grid point, we now basically have a multi-decadal time series with a resolution of just a few minutes of what's going on with the water elevations and the waves. So it's as if we've gone out and instrumented all of Tillamook Bay and the outlying waters with tons of tide gauges and wave gauges. So this gives you a really rich data set that you can look at. And so here we're looking at, for the historic case, what the total water level, which is the superposition of sort of the tidal signal with waves, and significant wave height. And this is kind of a curious looking signal because it looks like it's truncated here. The reason for that is because the grid point that I'm showing you is one that lies slightly above mean sea level. So as tides go in and out, it intermittently wets and dries. So that's what we're seeing here. And then you can see in the significant wave heights the annual signal in terms of the large waves coming, okay, each winter. This is the same grid point in the future, all right, and it looks a little different, and that's because now water has gone up, so this point is now wet more often, okay? And also there's somewhat of an increase in the significant wave heights at this particular point. So that's just at a point. Now, what we did is we sort of took kind of a ring around Tillamook Bay, and we looked at all of the grid points that lied from 1 meter above mean sea level to 2 meters below. So we're looking at kind of the fringe, if you will. And we took those grid points and we binned them by depth, and then we also sort of broke them apart into the southern half of the bay and the northern half of the bay. And what we're showing you is essentially for different return periods the total water level that's going to be experienced. And there's a couple of things to notice. Let's look down here at panel C, for example. So these are the points that are shallowest, and this exacerbates this effect. We see a very significant difference between, the red is basically the southern part of the bay, and the blue is the northern part. So we see a significant difference between total water levels in the south versus the north, and there's two reasons for that. Tillamook's got a long fetch from south to north, and in the winter you get large storms blowing from the south. So up on the north, number one, you're generating fairly substantial waves inside the bay. But in addition to that, you have a storm surge, which is a sort of time invariant setup of the water surface, which is due to that wind stress. So there's a pretty sizable difference spatially. Now, if we come up to the top panel here, let me sort of draw your attention to the blue lines, which are the northern part of the bay. And the solid symbols the solid line is basically the historic calculation of total water levels, and the dotted line is the future. And so what we see here is about a 20 centimeter increase in total water levels. Now that is riding on top of the sea level rise signal. All right, so if you're interested in things from a flooding perspective, you have some sort of sea level rise component, but now we have something else which comes from the physics inside the estuary, the nonlinear changes to the tides as the estuary deepens and so forth. So to kind of sum up, we really have kind of two main points here. I think, first of all, there can be significant spatial variations in water levels, whether instantaneous, some sort of total water level return period metric, whatever you're looking at inside of estuaries. And then also estuaries can respond in sort of interesting and highly nonlinear ways to sea level rise. So why does that matter? If you're interested in, this is sort of a typical flood map product where you have blue is kind of the contemporary 100-year flood, and then you have plus a sort of a moderate amount of sea level rise and plus an extreme amount. Those are the yellow and the red. This has been traditionally done using a simple bathtub approach where you sort of, you have your DEM, you have some established value of a flood elevation, and then you say, okay, in the future, 50 centimeters of sea level rise, bring that up, just intersect that new surface with the DEM, and there's your new flood line. Okay, and so the work that we've been doing is sort of, I think, suggesting that there are different ways to do that that are going to be much more accurate in terms of capturing where you may have increased flooding, where you may have decreased flooding. Okay? So thank you very much.
Hi, Dave.
Hi.
So when you showed the output from the combined model of snow model and hydro flow,
Oops, sorry.
it indicated that you were not capturing the peaks, the peak flows, although you had the timing really
Yeah,
well.
right here.
Yeah, and so I guess you'd probably be underestimating those extreme events?
Yeah, and so what we also did some sort of sensitivity studies where, for example, what we did is we just turned off every effect except stream flow because we were interested in, if you run Tillamook Bay with just like strong flood flows coming in at the various streams, what does that do in terms of creating a backwater? And so we can see that. And if we're a little bit low, then yeah, that we might be somewhat underestimating that. The reason that I'm not too concerned about this figure right here is that, let me think about this for a moment. This was done, I'm trying to remember how we forced this particular simulation. We didn't do any bias correction with this, and the calibration with this we didn't really worry about too much because in the end we knew we were just going to force it with NARCAP, and we were looking at the changes from historic to future. So,
Wondering if you had a sense of why the model was missing the peaks. Is it
it's because of the NAR data, and this is being forced with NAR data. That's right, and we made some comparisons between the NAR data and actual data, and it's not perfect, but we didn't really worry about that because we don't have anything else. We don't have anything else we can do with that NAR data. So it's the input side of things is what we're hanging our hat on, is that the precip from NAR is just not high enough in this area. That's a very good question. The computational resources that went into this were very considerable. And I'm surprised nobody is asking me the question of like, why did you just run one GCM sort of? because all these talks that we've been seeing today, people are running 15 and averaging them, and that's a fantastic thing to do. That would be a bit prohibitive with this. And so this was kind of almost like a pilot study for what can we do as a ratio of what can we get out of in terms of the effort that goes into it. And it's given us a lot of ideas about moving forward. For example, if we're interested in flooding products, we are simulating much of the year where total water levels aren't that significant, right? And so one thing you could do is constrain this to just modeling winter months to get those extreme events. Another thing that you could do is to sort of look at some more statistical approaches where we know that big offshore breaking waves are a big part of forcing these water levels in these estuaries. So if we could do some sort of connection between like large wind events and connecting those to wave heights, that's all that we need. So if we have a quick way that we can run different climate sets and grab information about extreme wind events, we can then turn that into wave heights, and then we know as those approach shore and they break what sort of super elevations those are going to give us. So moving forward from this, I'm not sure it's the best strategy to sort of do in some systematic way where we use a sledgehammer and try and run 10 different GCMs. I think that what we need to do is take what we learned in terms of what are the main contributing physical processes and then dial in on those and spend the effort there, where you could very systematically run lots of different climate sets quickly, and you could very quickly transfer from one estuary to another. Yeah.
I'm Zhao Qingyan from PNNL, and so for your projection for the future significant wave height simulation, how many model runs have you conducted for the future? Is it a lot of ensemble runs, or actually just?
We used, kind of to the question that was just asked, so within the NARCAP product, within the NARCAP database, there's a sort of a rather incomplete matrix of about, I think, 5 or so GCMs dynamically coupled to about 5 or so RCMs, and we used a single coupling there.
Okay.
And
so
that's a big issue of uncertainty, because if you look at the literature on Pacific Ocean wave heights using GCMs, the studies that are out there there's zero agreement in terms of the results. You have some that predict increasing, some that predict decreasing, some that predict no change.
Yeah, because the wave prediction itself probably has, in terms of errors, it's probably can up to, maybe 20%.
Mm-hmm.
In terms of variance. So another question is, you have been mentioned about the extreme storms in the future. So, but based on, I really questions whether you see that actually in the NORCAP product in the future, the wind actually you see increase in terms of extreme storm event, because based on Cliff Mars's yesterday's talk, actually we don't really see it in the Pacific Northwest. So.
Right. I mean, like I said, you see different results, and so it's not. Whereas the agreement with things like temperature and precipitation is I mean, those models are much more converged. But when it comes to winds, and then of course taking winds and running into waves, quite a bit less agreement.